Okay guys, in this video I will discuss about different failure pattern of bracing. Okay, so if you are new to this channel, please do subscribe and also don't forget to press the bell icon so that in future you can be benefited. Okay, so at the very first, assuming you are a beginner, the basic function of a bracing is to carry the lateral load. Okay, so let's say you have a frame, there is no bracing. Okay, so in that case, if you have any lateral load, definitely the frame is stable if you have provided all these connections as moment connections. Okay, so in this case the problem is that the deflection is much larger. Okay, and in all of the sophisticated structure like pipe rack and other structure, you know that this lateral deformation or this drift is not much allowable. So in that case, what is the solution to reduce this drift or lateral deformation? Simply you can put a bracing, or you can simply put all this connection as pin connection and then put a bracing like this. Okay, now if you provide any lateral load, it will be transferred like this, then it will come to this joint, finally through this bracing it will come to this foundation. So basically all these columns are load free. There is no contribution of column to carry this lateral load except supporting this bracing. Okay, so basically the bracing is under the action of tensile load for this particular diagram. Okay, now let's say you are applying a lateral load from this direction. Okay, so just let me clean this one. Yes, so let's say you are applying a load, lateral load like this, and in this case let's say all these joints are pin joint, there is no lateral load in this side, and you are supposed to provide a bracing like this. So in this case it will directly transfer to this foundation through this bracing. Now this bracing is under the action of compressive load, and initially this was under tensile load. So basically you can design a bracing for two type of load. First one is tensile load, second one is compressive load. Okay, so definitely all the failing or all the failure pattern are mainly because of this tensile force and compressive force. Now look into the failure pattern due to tensile force and compressive. Let's say instead of having a single story, you have multi-story like this, and in all of the story you have provided the bracing to carry the lateral load, just like this one. Okay, so at the top of this multi-story frame you have provided a lateral load and you have provided X bracing like this. So you know that this lateral load is going to be transferred through this strut to this point, then through this bracing, then to this point, then through this bracing to this point, like this. Okay, so here the basic assumption is that all these bracing are designed for only tension. That is why only this bracing, this one, this one, this one, this one, and finally this one, they are carrying the lateral load. Okay, because the basic assumption is we have designed the bracing only for tension purpose. So due to tension, you know, each and every member, what will happen due to this tensile force? Initially there will be some yielding. Okay, initially there will be some yielding, and finally if the tensile force is crossing the yield stress, it will rupture like this. Okay, so here is also first this bottom one is started to yield. Once it has started to its yield point, then the second story bracing has started to yield, and once it has also completed its yielding, then the third story started to yield. Okay, so this is the mechanism of failure progression, correct? So now come to the point of failure. Here you can see due to the tensile force, the main type of failure is the yielding. Okay, first one is the yielding, second one is your rupture. Okay, and all of this can happen to the member itself. As in this picture you can see, here has a rupture has occurred in this member itself. Okay, And in many cases, you know that the member itself is strong enough. The weakest part of any structure is its connection. Okay, right? So here you can see that the connection is strong enough, but as the member was weak, so it has failed first due to yield, then it has simply ruptured. Okay, but let's say the member is strong enough, as in this picture and in this picture. The member is strong enough, but the connection is not strong enough to carry the tensile force. So in that case, what will happen? Simply your member connection will fail. Okay, so here you can see the gusset plate has ruptured. Okay, and in this case, here you can see that the connection has failed, but not the gusset one. The gusset one is intact. Also, the member one is also intact. Actually, the failure has occurred due to block shear. Here you can see that this was the angle and we have provided the bolt like this, and the failure has occurred in this bolt line. Here you can see this is the bolt line failure, and this is due to block shear failure. That is the reason you should check each and every checking from connection design to the member design, whether it is going to fail in member yield or member rupture, or in case of a connection failure, whether it is going to failure due to the block shear or gusset failure. You have to check each and every one whenever you are going to design your bracing for tensile force carrying member. Right? Now come to the second point, that is, let's say you are supposed to design the bracing for carrying the compression or the compressive force. Okay, so in the compressive force, you know, if you have any compressive force member like this, the major failure is due to the buckling. Okay, so let's say this is the gusset, this is the frame, and you have provided a bracing like this, and this is the lateral load. So this is under the action of compressive force, right? So the basic failure mode is due to the buckling of this member. Okay, and you know that buckling stresses depend on slenderness ratio and the yield stress of the material. Assuming the yield stress is constant, you have only two parameters to play with the design. First one is that effective length, and second one is your radius of gyration. You know that once we have reduced the slenderness ratio, its buckling load carrying capacity increase. So to reduce this slenderness ratio, what you can do? Either you can reduce the effective length or you can increase the radius of gyration. Very simple. Radius of gyration increase means you have to use higher section instead of a lower section. Let's say instead of using ISMB 200, you may have to use ISMB 300. It's a higher section that is costly. So to increase the radius of gyration, simply you can increase the size of the member. That is one solution. Second one is you can reduce the effective length. So to reduce the effective length, what you can do, instead of providing a single bracing from end to end, you can provide a cross bracing like this. As you can see here, the brace has crossed here. Okay, though it has failed due to buckling. Here you can see it has failed due to buckling. So even after reducing the effective length by providing this cross bracing, if your bracing is failing, then the only way to resist is you have to increase the section size. Okay, so that's it. If you love this video, don't forget to share it.